Today in this lecture we will discuss about the partition function for continuous systems, Gibbs paradox, and how do you remove that Gibbs paradox. Okay, so in the previous few lectures we have been talking about the partition function, and which we had we had an expression for that, then how partition function is related to other thermodynamic quantities of the system. So here let us discuss about the partition function for continuous system, where the continuous system means here, so in classical mechanics or in classical statistics, that we consider the systems with this systems having continuous energy, meaning so this energy states of, or the energy levels of the systems are so close to each other that we can almost assume that to be a continuous, so the energy takes continuous values. Okay, so we have defined the partition function z by this expression in the earlier videos, which z equal to sum over I. So I goes from the all face cell, then gi is the degeneracy, right? So the number of zones, or the number of cells within the zone having say similar energy, and then e to the power ei by kt, where k is constant and then T is the temperature. So we have to convert this discrete looking partition function, okay, from sum to a continuous values of energy. So I have to transform this, basically what we need to do, we have to transform this summation to a integral and other terms as well. Okay, so for that what we will do, we will have to, so the energy goes from 0 to infinity. This g becomes so g of e dE, and then this expression remains as it is. Okay, so this g of e dE represents, okay, it's the number of states, okay, number of states lying in the or the number of states having energy E. Okay, well, if I talk if I take GE dE is the number of states having energy E2, so somewhere in between E2, okay, E plus dE. So how many states are present from this range? Okay, so that is given by this G of E dE. So we need to, so before going further, okay, so we need to find out an expression for this such that we can carry out the integration, because see we have been writing this gi or g of e, but then we do not have any expression for that. Okay, so first idea for all the, like, first thing to find out here is to get an expression for this particular term, right? So how do I get that? Okay, so GE represents what is number of states having energy between E and E plus dE. So we need to somehow get the number of states lying in that range of energy. So then first we will calculate the number of microstates, okay, in phase space. So phase space, as you all know, it consists of, like, if you think about there are mutually perpendicular momentum axis, and then the position or the coordinate axis. So the volume of entire phase space divided by volume of a single phase cell, which we know the h cube, okay, then it will give you the total number of, or the number of microstates in a phase space. Okay, so now, so you have to integrate over entire space to get the volume of the phase space. So that is given by, so you have to integrate dx, dy, dz. This is the space, or the coordinates, or the position coordinate axis. So we have to integrate over entire volume for that, and also the momentum space. Okay, in the momentum axis, so you have to integrate over all three mutually perpendicular momentum axis. The space over, or the space spanned by this three mutually perpendicular momentum axis. Okay, so let us just write for this the space for this or the space covered by this for position coordinate axis, or the coordinate axis is, let's say this is given by V, and this is so a volume of single phase cell is h cube. Okay, so now I need to understand this particular part. Okay, Now the momentum, we can write that p square is equal to px square plus py square pz square. Okay, so and this is related to the energy p square. If we remember, so E is what? P square by 2m. Okay, so now from here p square equal to px square plus py square plus pz square. So you can think about a sphere. Okay, so let me just draw a, okay, okay, one more axis. Let me just okay, so then just think about this. Uh, these are px, pz, all these three axes. Okay, so this is, let's say, px, py, the pz. Okay, so this three axis, so the p square represents, so that you can think about there is a radius r. So the radius r here, you can think about the p. Okay, so this is your, like, this expression represents a sphere in a three-dimensional space, so the momentum space, okay, with having radius of p. Okay, so I can draw a sphere. So okay, let me just I have to need to be careful about drawing this. Okay, I need a center here. Yes, so think of, and this represents, this radius, the black color line here represents the radius, which is p square. Okay, sorry, this is p in this case. Okay, so the position vector is given by this px square plus py, or the magnitude of the position vector. Okay, let me use some different color. Okay, so this is your p. Okay, this is your p. So this expression represents a sphere having radius p. Okay, and its position vector, as you can, magnitude of the position vector, you can calculate p square. Okay, so this magnitude of this line, you can think about, is p square equal to px square plus py square plus pz square. So this is a whole sphere with radius p. Okay, so I need to calculate the volume of that entire space. So this is sphere. So the sphere's volume is given by 4 by 3 pi r cube. So r is here, the radius cube. So radius is p here. So that's why we have this p cube. Okay, so, and if I need to know about, let's say, the momentum, the number of states lying in between momentum p and p plus dp, then I can draw another sphere with radius p plus dp and then calculate number of states in between that. So we are not going to going by that. We'll stick with this expression. So the number of microstates in a phase space we can calculate using this expression. So the volume of the phase space is given by, so the integration over all three dimensions of the position coordinates, which gives me the v, and then the in the momentum space the p square, which is equal to px square plus py square plus pz square. So that represents a sphere, okay, with radius r. So its volume we can calculate by using so a standard formula that we know, 4 by 3 pi r cube, or the radius cube. Here the r is p, so that's a p cube. Okay, divided by h cube, which will give me number of microstates in the entire phase space. All right, so now, since we know that energy is related to the momentum by this expression, energy is equal to p square by twice me. So I can write p equal to 2me to the power, so square root of that basically. Okay, so square root of 2me. Okay, so now substitute this value of p in this expression, and then we get this, okay, 4 by 3 pi p cube. So p is square root of twice me. So now we were after this particular term, g of e dE, okay, or you can think, if you are or I need this GE DE, anyway we can write later on. So GE is the number of states, okay, which are having energy E. So what we have to do here, so the G of E is equal to, so here see the number of state microstate is represented by omega here, okay. So this will be given by d omega. So if I differentiate this omega with respect to E, that is energy, we will get G of E. So it's okay. So like, you know, it's giving you a density of states, meaning it's like number of states lying at a particular energy, or to be precise, actually we need to talk about this, the number of states whose energy is in between energy E and E plus dE. Okay, so that will be given by d omega by dE. So if I calculate out this expression, differentiation, so I will be getting G of E V by h cube cross 4 by 3 pi, okay. So 2 by 3 will be coming out, and I will remain with, so remain with 2m e, anyway this is constant, okay. Let me get this little bit this side, okay. So 2me, then I will remain with e to the power half. So for that, you know, now simple math, 3 will get cancelled out, this 2 and this will remain at 2. So I will be having, so G of E will be given by V by h cube, so 2 pi, so 2 pi will be remaining, and then 2 to the power m and e to the power half, okay. So I will have, so I have got the expression that we were looking for, this G of E, okay. So yes, this is same as this, such that this 2 pi and V is written together here, okay. So yeah, so this is pretty simple, okay. So G of E, I have got this 2 pi V by h cube, and then twice m to the power 3 by 2 and e to the power half, okay. Then you, using this expression, now substitute back in this. So then you just follow basic steps of mathematics, and then using, so you will be getting this particular term, okay. So now using standard integration, which one of them I have discussed in one of the earlier videos. So then substitute that standard formula of integration, then you will remain with this, and here this 2 will get cancelled here, okay. And then you can take out, so the pi, there is pi square, sorry, this is pi, square root of pi, so that can be taken out. So this 2, and then this is square root here, this is pi, so that will combine, will give you pi to the power 3 by 2. So you can combine all this term within this 3 to the power, meaning the within bracket, and then write to the power 3 by 2, and then I will get expression for the partition function z with having continuous energy available in terms of temperature now, okay. So this is a single particle partition function, okay. Now it's quite interesting if you take this ideal gas or the ideal system, okay. So the partition function for a monoatomic gas consisting of n molecules will be equal to simply z to the power n. So if single particle partition function is z, then if the system consists of n molecules, okay, so then the partition function for that function will be simply z to the power n. Now let's just try to look at a very simple system having, like, let's say two particles n equal to 2, and let's say there are 2 energy levels, okay. Pretty simple. Two energy levels. Okay, two energy levels. Okay. So let's say these are two energy levels. Okay, then the first ground state or the first state is, let's say, script E1 energy, and it is around E2. So there are two particles. So both, see, there are how many ways we can distribute these two particles in these two energy states. Let's try to look at. So first step could be like, no, both the particles can be in the both this E1 state. There is a ground state. Think about this is one way. Okay, let me just distinguish between like this. Okay, this is one way. Second, it could be in down state, and one could be in the let's say excited state. Okay, and we can interchange these two particles. Okay, now see here, this we are talking about, let's say this is number 1, number 2. So number 1 is in ground state, number 2 in ground state. In the second case, it could be like, particle 2 will be in the ground state, particle, let's say, 1 will be in the upper state. Okay, and in other case, the fourth case could be the both the particles are in the upper state. So there are 4 ways you can distribute these two distinguishable particles, let's say. So this is number 1, number 2. Okay, so now let's try to write the partition function for that. Okay, so the single particle partition function we already know, right? So single particle will be given by Z. So there are two energy states, one particle. So let me just repeat here, some I, then gi here is, we do not have any degeneracy, so it will be simply e to the power ei by kt. Okay, so for single particle it will be two energy states, so e to the power epsilon 1 by kt plus e to the power E2 by kt. So this is our single particle partition function. Okay, now for two particle partition function, let us write. Okay, let us use green. Okay, so in that case, let's say in the first case, so the partition function for the system with two particles, I can write with having the two level energy system, Z2 will be equal to, so the first case both the particles are in E1 state, so it will be twice E1 by kt. In second case, one particle is in first one and like in the E1 state, another one E2 state, so it will be E minus, so E1 plus E2 divided by kt. Okay, and then the next term will be, again the second case will be the first particle is in the higher state, high energy state, and the second one is the lower energy state. So again energy will be E2 plus E1, okay, divided by kt, then plus in the last case it will be both the particles are in the E2 state, so I can write twice E2 by kt. So this is, we can write E1 by kt plus this is same, this two terms is simply, you can sum it up because exponents are same, E1 plus E2, then E2 plus E1 is the same, so twice E1 plus E2 by kt E2 by kt. So see, this I will end up with, so this is like a plus b whole square kt square, okay, twice ab you can think about, which is as good as saying that whatever z I have written here, z square, isn't it? So this can be, you can extend it to any number of particles and you can carry out the maths. It will be like this. Okay, so if I have single particle partition function, then for n molecules or n particle partition function will be simply for z to the power n. Okay, so let us proceed with the discussion. Okay, so the entropy for an ideal gas, we all know that, and so we have calculated this expression in the previous video, where entropy is given by nk ln z plus 3 by 2 nk. So now substitute for the expression of z that we have derived just few minutes back. Yes, so this expression which I have derived, so let's substitute for z here. Okay, so if I substitute and then expand this particular term which is combined with so many terms. Okay, if I combine it, because I have this ln here, so you can expand. So if you take, you will be getting with this. So what I do here, this ln v, then ln m, this I keep these terms, ln t is the temperature, and here all the terms are constant. Okay, so and if you take this nk to be common, this 3 by 2 is also there. Okay, so I take, simply I can write some constant alpha, or simply I can write constant terms. So because these are, even if the system changes, so this constant will remain constant, irrespective of whatever the systems are, meaning the values of these things will remain constant. Okay, so I will remain with the expression for entropy. So nk ln v plus 3 by 2 ln m, and then 3 by 2 ln t. Okay, so now what we do, we take two systems. Okay, we are now trying to understand what is Gibbs paradox. Okay, so let's take two systems. Okay, now this is going to be an interesting one. Let's say, okay, all right, so I take two systems, but which are separated by, let's say, a partition. Okay, and this is, let's say, system A, this is system A, this is system B. Okay, and system A has got an A number of particles with volume VA, and then mass of each particle is, let's say, MA, and it has got temperature TA. So then automatically the entropy will be SA. We can calculate from the expression that just now we have discussed. Similarly for B, let's say we have NB number of particles, volume is VV, the mass is MB, then entropy is SB, and the temperature is TB. Okay, so for our discussion we will consider that both of them are at thermal equilibrium. Both this system A and B are at thermal equilibrium, meaning, so this TA equal to TB equal to T. Let's say they are at some constant temperature. Okay, so these are ideal systems, both of them. Okay, so what our experiment is, what we are trying to understand here is that we'll calculate entropy of this system A, entropy of system B. So when I remove this partition, okay, so the system has got particular I mean the variables to define each situation or each condition. Okay, so once I remove the part, so I will calculate entropy for system A, system B. Since entropy is an extensive quantity, what will happen if I remove the partition, then both the system get mixed up and it become a single system, and I'll try to see what happens to the total entropy of the system. So ideally what happens, entropy of the system A plus entropy of the system B must give you the total entropy or the combined, or the entropy of the combined system. And let's see what happens. Okay, and as we go along you will see, for simplicity we will remove some of these barriers, like Na, Nb, all will take out to be same number of molecule and things like that. Okay, now let's write down the entropies of the two systems. Okay, we already know from the previous expression. So SA is the entropy of the system A, which is Nk ln Va 3 by 2 ln Ma. Ma is the mass of the particles in the system A, and Ta is the temperature Ta of the system A. Okay, so similarly for the system B, so as I said, we will take systems to be in the same temperature, they are thermal equilibrium. Then this Ta equal to Tb, which I can write simply Ta, the Tt. Okay, so I have replaced Ta and Tb with the temperature T. All right, remaining things are same. Okay, so now let's as I said, the entropy is the extensive quantity. So the entropy of the total system SA must be given by SA plus SB. Now let's see what happens is that if we remove the partition. So as I said, we have taken the system, this system A and system B. So, and it has got definite number of particles in the system A which are same meaning, and again in the system B a definite number of particles. They are ideal gas molecules you can think about, and we will slowly remove the partition. Okay, what will happen if the volume VA and VB, it will become now a VA plus VB, and the total number of particles will be simply Na plus Nb. Okay, let's see what happens to the entropy of the combined systems. Okay, so if we remove the partition, it must be equal to the sum of the individual entropies of the system. Okay, let's try to see what happens. So if I just substitute back the entropies of the individual system, the expression for entropies of the individual system, and I am remained with this. Okay, so now let's simplify the problem. Okay, let's take these few conditions that VA and VB are equal. Let's say these are volume V. Okay, similarly for the mass of this particle also we can think about these are same. Okay, so here actually VA VB equal to V. So this is for our simplicity. Okay, just to understand the problem. And Na, the number of particles in A as well as in B are same. There is total number of particle is N, there is a capital N, and mass of each of the particles also let be same. Here it is not written, but you can include here. Okay, so mass of Ma is equal to Mb equal to, let's say, M. Okay, so and then anyway we have considered the temperature of both the systems are same, constant, so they are thermal equilibrium we can think about. Okay, so now the entropy, the expression for entropy of both the system becomes same. Okay, Na, this is, so there is no subscription, this A subscript or the B subscript, so all the entire, so the expression for the system A and B both are same, so the total entropy must be twice of this. So if I replace here by 2, sorry, I just if simply I add, like multiply this, add a 2 here, then our the entropy of the combined system should give me that expression, right? So now, so the SAB, the entropy of the combined system, should become this. But now let's now consider the system as a whole, not as A plus B, as a whole system, because I have now individually volume had been V, so it will be replaced by 2V. Number of particles individually it was N. Now the combined system will have twice N because I have removed the partition, so the particles from both the system will get, they will try to mix up, so they will diffuse from the one corner of the system to the other corner, so it will start mixing up. Okay, so now so instead of looking from the system A and B and trying to calculate the entropy, now let's look the system from it's combined as a one system, and then try to calculate entropy of the combined system, where I know number of particles is now twice N, and then volume of the system is twice V. So in that case, an entropy expression is the same, right? We have derived. So you replace N by, so wherever it was N, replace by twice N, and wherever there is V, so you replace by 2V. So while doing so we get this expression. But now, see, we need not worry about this particular term. But then the interesting part is here, twice Nk, then ln 2V. See, ln 2V, I can write this ln 2V, okay, ln 2V can be written as, ln 2 plus ln V. So ln V term is here, and this, because it's multiplied by twice Nk, so twice Nk ln 2 term is written here. Okay, but if you compare now this expression, okay, let me just clean up a little bit, then it will be clear to see. Okay, now put attention to this particular term, and these two terms are same. Okay, but then this S dash AB, which is the entropy of the combined system, when I look at these two combined as a whole, not as a individual sum of two individual systems. Okay, so I am now looking at the system as a whole. Then see, in the entropy expression I get the extra entropy. This is an uncountable, extra entropy term we get. Now this is now puzzling, because we had individually two systems, and when we combine them, we know that entropy is the extensive quantity. It must give you the sum of the so the entropy of the combined system must be equal to the sum of the individual entropies, right? That's what we expect. But here, as we have seen here, that in the entropy of the combined system expression, there is an extra term. Now, where does some extra energy or the entropy has been generated here, as stated by this particular expression. This cannot happen. Okay, so this is known as Gibbs paradox. Okay, why this, or how this extra, or like why this extra entropy, there is some extra entropy comes out in the entropy expression of the combined system. Okay, so this extra term, or this entire the mismatch of the entropy, when I calculate from considering the individual system and as a combined system, the entropies of the both way do not match. Okay, so so this is known as Gibbs paradox. Okay, now idea is to, how do I remove, where is the problem? So see, just to get this idea, we had two ideal systems. Okay, the system which consists of ideal gas, you can think about. So okay, so the system A and system B, both of them had got same number of molecules, and also the volume of the system is same. Okay, we have calculated individually the entropy of the individual systems, and as we know from our thermodynamics, that entropy is an extensive quantity. So the entropy of the combined system would be the sum of the individual entropies. So while doing so, for this case, we have seen that the entropy that we get by combining each of the entropies of the system, that is less than what we get when we consider system as a whole. So as a combined system, we have twice n number of particles, and the volume is twice v. Okay, so in that case, we have seen that there's an extra entropy terms comes out into the picture. So this is known as Gibbs paradox. This is okay. So then there were few physicists. Okay, actually one of them is physical chemist who had worked on this problem and try to resolve this Gibbs paradox. Okay, so it was removed by this physicist Martyr Tetrode and an Otto Secker. So this two, so actually Tetrode was physicist and Otto Secker was a chemist, actually physical chemist, and they had solved this problem, what is known as through an equation, or we will derive this equation. Okay, Secker Tetrode equation. All right, so where was the main, the hidden information that we could not catch when we are trying to discuss Gibbs paradox? Okay, the idea there was that systems are same in the sense system A and B had got similar, so to say, indistinguishable particles now. So when let me just draw the system here. So we had the system A and B. Okay, system A and B. So we had n number of molecules, volume V. So when they start, so when you remove the partition, okay, so let's just remove the partition. Let's say a little bit remove. Okay, so when I remove the partition, the molecules from A side will go to B side, and from B side will come to this side. Okay, when they start mixing up, okay, so actually which particle is going to which corner of the system is indistinguishable. Meaning, if I have two, let's say, indistinguishable particles, these are position 1 and position 2, let's say. So if I interchange this particles position, actually we cannot make out that we created a new state. Okay, that was the problem here. So systems are same means that both system A and B are, they are alike. Okay, so what will happen? So while counting the number of microstate for the system, actually see there are n molecules in both of them. So we have, so earlier we had this expression for counting the number of microstates, but now since systems are same, so actually we are counting, our counting more number of microstates than what is actually the number. What actually is the number. Okay, so this n factorial we have to get rid of in the system of schemes that we are trying to talk about. Okay, so since there are n particles, so there will be n factorial ways we are counting more than what is required for our system. Okay, so these are unnecessary counting we are doing. So that's why, because we have n number of particles, so then I will create n factorial terms which are we are counting more. Okay, so actually these many terms we will not be able to distinguish from each other. Okay, so that's why we have to divide in the W expression by n factorial. Okay, so when you our number of microstates will be reduced. Okay, so it's like, we are trying to talk about two systems. When we combine them, it become one. Even though we were, system 1 and 2 are independent of each other initially, when they combine, so the number of particles will increase, no doubt. But then because the molecules are similar to each other, so the number of microstates will not simply get added up or meaning get multiplied. So it will be reduced. Okay, because of this indistinguishable nature of the particles. Okay, so we have to divide the W by n factorial. That's what the highlight of the story here. Okay, so then expression for this ideal gas, the entropy expression. So that we had from Boltzmann canonical distribution n k ln W. So earlier we had calculated this expression. Now what you have to do, you have to divide it by n factorial, whatever we have calculated earlier. So then that will give rise to me this extra, because it is in the denominator, minus nk ln n factorial. So this is the extra term will appear in the entropy expression for this case. Okay, and then using Stirling approximation, I will get this n ln n minus n, and then this particular term I will absorb this nk, I can take common ln n, so ln n is being absorbed here. Okay, in this first term, and I will remain with, this is negative, this is negative, it will become positive nk, so I will be having this. Okay, so if I combine both of them, so I will be getting this expression. So this is the expression for entropy of a system which is having n number of molecules, so identical, also the indistinguishable molecules. Okay, and this entropy expression is known as your Secure Tetrode equation. This is the expression for entropy. Okay, now let's use this system. So now the system we had A and B. So the combined system, if we talk now, so system A had got same, and because the volume of the system A and B are same, number of particles is same. So if I combine the SAB, which is equal to SB, and this is which is equal to twice S actually, right? Because N is same, V is same. Okay, so and then when I calculate the entropy for the combined system, which has got like twice n number of particles and the volume V after removal of the partition, then we will be getting, so see this n is being replaced by twice n here. Okay, so the V and n will be replaced by twice V and n. See, the important thing here, here instead of having the total volume what we had in the earlier expression, now we have volume per unit like molecule, or volume per particle or per molecule, which actually does the job for us. Okay, so twice V by twice n, so 2 will get cancelled out. Okay, so then this is again a simple substitution, as you have see here and here. This expression what we get here is the entropy of the, so this 2 will get cancelled out, the entropy of the individual system, what we had here earlier. Okay, this is Secourt-Tetrode equation. So then this solves the problem. The sum of the entropy of the individual system gives rise to actually the entropy of the combined system. So this is how the Gibbs paradox is resolved. So basically we had this extra number of microstat that we had counted for when we had this systems with having indistinguishable molecules. Okay, so this brings to me end of this Gibbs paradox.